Today, I'm going to be talking to you about cartilage, which is this fun material that, well, it's found in a lot of places, but the one that I'm going to talk about is the kind that lines your bones and forms your joints. So it is, oops, right over the top of your bone interfaces. And then there's a small space in between the joint space. So here's your articular cartilage. And then you have your joint space, which is fluid filled. And so the purpose of your cartilage that is lining your bones is to act as a hydrodynamic cushion that resists compressive forces. So if you think about walking around, you're constantly putting compressive loads onto your bones, and that is also going onto your cartilage. And the cartilage is taking on some of that compressive force. It's absorbing shock. So if you were to jump off of a table instead of walking around, you're going to generate a higher impact load, and the cartilage helps to absorb some of that shock, and then it transfers some of the load over to the bone. So let's take a look at what this material actually looks like and some of the gradients that are incorporated into it. So if we just go ahead and draw a cross-sectional view. We find lots of different layers. So if you think about a gradient implies kind of a continuous changing throughout, but you can almost kind of break things up into layers as well. And so that's what we'll do with our cartilage. So at the top, we have our articular surface. So this is the part that is interacting with the synovial fluid in the joint space. And then right under that, we have the superficial zone, which we'll number as 1. Then we have middle, and that one's pretty big. And then we have the deep zone. And then calcified cartilage. Directly under that is the subchondral, so undercartilage bone. And so how I'm going to go about drawing this is there's a few different components that we want to focus on. So I'll draw each one at a time with different colors. So to start, we'll start with the collagen, which makes up a bulk of the extracellular matrix. And in the superficial layer, the collagen is actually parallel to the surface, and it's pretty dense in this layer as well. And this collagen diameter is pretty thin at the top. And then as we move down into the middle layer, the collagen diameter actually gets thicker and it's aligned obliquely. So you can kind of tell from this arrangement that the parallel would help to, on the surface, to resist wear and shearing forces, whereas the oblique might help as a first line of defense against compressive forces. And then the collagen gets even thicker as you get down into these deep and calcified layers, and it looks like this. So it's arranged perpendicularly. And this actually extends all the way down into the subchondral bone, which helps to anchor the cartilage and bone together so you don't get delamination of the two layers. And so we can actually then think about this collagen as a gradient in this direction, right? The collagen diameter is increasing. But collagen is not the only thing that makes up the extracellular matrix of cartilage. It is a really important part, and it helps to keep structure. But proteoglycans, which are these protein and sugar conglomerates, also exist within the cartilage, and they attract a lot of water. And so you can think of cartilage as kind of this squishy, jello-y kind of thing. And the reason that it has so much water is because the proteoglycans are retaining it. And so in this superficial layer, we have a little bit of proteoglycans, not a whole lot. And then we get more as we go into the middle layer. They're just arranged randomly. And then in the deep layer, that's where we have the most. So lots and lots of proteoglycans. And so again, we can think of that as a gradient, but this time it's the proteoglycan concentration that's increasing as you go through the layers. And like I said, proteoglycans hold on to water, but they also take up space. So the way that the water concentration looks throughout these layers is the superficial has lots and lots of water. It has less proteoglycans, but the water from the proteoglycans below is kind of retained up there. And then the water kind of decreases in concentration as you go down. You have more proteoglycans, but they're taking up space. So the gradient that we get then for the water concentration is the opposite of the proteoglycans. So water concentration. And there are cells throughout this, they're chondrocytes. Um, they kind of align themselves within the matrix accordingly. So in the superficial layer, they are in the same kind of flattened state as the collagen. In the middle layer, they're really rounded, just randomly throughout. And in the deep layer, they almost form these columnar orientations. And then the other thing we can think about for a gradient here is porosity, which is very similar to the water concentration. It's more porous at the top where you have more water being held. And so if we think about then the mechanical properties that each of these layers would provide, the top is really low friction and the collagen alignment prevents wear and protects from shear stresses, but it's easily deformed. So if you think about putting a force on this top portion here, it can deform a lot. And when that happens, the pressure in the water is going to increase. So hang on. Force causes increase in pressure of the water. And eventually that increase in pressure will actually cause water to flow out into this joint space here. And then this secondary layer provides a first line of defense against compression. So that collagen arrangement kind of helps to take some of that compressive force. And then as that water is flowing out, these proteoglycans start getting closer and closer together. So we get kind of like pushed up against each other, but they are highly negatively charged. That's why they're attracting so much water. But when the water disappears and you get this right next to each other, those negative charges do not want to be next to each other. So they electrostatically repel each other and you get some compressive resistance in that way as well. And that continues down into the deep layer where you have that higher concentration of proteoglycans, you're getting more resistance to compressive forces. And then this calcified layer in the fourth part is really there to kind of transition into the bone. So it has some calcification in the same way that the bone below has a lot of mineralization, and it still retains some of that cartilage-like features so that it transitions and you don't get delamination of like two completely different layers next to each other. Or cracking, that's a place where cracking can occur as well. And then the bone below is vascularized and mineralized. So the cartilage itself actually has no vascularization. It's pretty thin, so you can get some oxygen that goes throughout the layers to the cells, but the cartilage doesn't have any blood supply to it. The bone does. So how do we model the biomechanical properties of cartilage? Well, it's actually a very viscoelastic material. So we can break it down. If we take this little drawing here, and we wanted to make more of an engineering model of what this is doing here, it might look something like this, where we have a spring, and it comes down, and we have a damper. And this spring would represent the elastic components of the forces, and the damper would represent viscous. So elastic equals spring, viscous equals damper. When we think about these components of the collagen that we just talked about, the elastic part would be all of those solid extracellular matrix proteins. So that collagen and those proteoglycans that are resisting the compression, they behave like a linear elastic solid. But the water, the fluid phase, that's a little more complicated. It has viscosity and it acts differently depending on how much time it has to act. So when you just smack down on that water, it's going to behave as an incompressible liquid. But the more time you give it and the more pressure that builds within there, it starts to move. and flow out like we discussed before. And so that time dependence is what makes it viscous and why we need to model with a damper as well. So if this is actually the Kelvin-Voigt model, and mathematically, we can think of it like this. So again, let's say we have a force here. Let's say we're walking, so force of walking. The total stress that's going to be felt in that cartilage is going to be the sum of that elastic component here and the viscous component here. And if we break that down in the way that we've modeled it with a spring, we know that elastic component is going to be the elastic strain times Young's modulus. But the viscous component is actually going to be the viscous strain times viscosity. And so the stresses that are being felt are the sum of those two components that are going on. But in actuality, that is a pretty simplistic model. A better way to describe it is the biphasic poroelastic theory, which still takes into account the linear elastic nature of the solids and the pressure buildup of the liquids, but it also accounts for drag using Darcy's law. And that is the frictional drag acting on the solid phase. So you end up with this equation that is the average velocity of the fluid is equal to the permeability of the solid. So that relates to the porosity gradient that we talked about before, times the pressure gradient of the fluid. So if you wanted to more accurately model what is going on with the mechanical properties of cartilage at every layer, you would want to also include this drag component.